Check it out behind us here. Arizona's ground is broken. We're talking earth fissures, major cracks in our desert that can open up at any moment.
But is your home or business at risk, and can we prevent these from happening? Well, the answer is yes and no. Our Brianna Whitney explains.
Deep in the remote expanses of the Arizona desert, a startling geological phenomenon has emerged. Long, gaping cracks tearing through the arid landscape with alarming precision and mystery. These earth fissures, some stretching for hundreds of feet and plunging dozens of feet deep, have seismologists and geologists alike gripped with curiosity and concern. Unlike the natural erosion or surface cracking that gradually takes shape over years, these sudden, dramatic splits in the earth appear almost overnight, slicing through dry valleys and disrupting the desert's otherwise tranquil surface with a ferocity that belies the calm environment around them. Before we start, smash the like and subscribe buttons for more updates. The discovery came as part of a routine aerial survey conducted over southern Arizona, where satellite imaging and drone footage revealed dark lines cutting sharply across vast stretches of desert floor. Upon closer inspection, teams on the ground confirmed that these weren't minor surface features. They were deep, potentially unstable fissures that stretched in irregular patterns, sometimes several meters wide, other times narrow enough to be missed if not observed from the right angle. These weren't merely cosmetic scars in the landscape. They pose significant implications for infrastructure, water movement, and the broader geological understanding of the region. Arizona has long been a region of tectonic quietude, far removed from the more volatile zones along the western edge of the North American tectonic plate. It is not a state traditionally associated with dramatic seismic activity, and the formation of such pronounced cracks presents a puzzle that breaks with historical norms. This dissonance between the region's seismic history and the magnitude of the current fissures immediately caught the attention of experts in seismic monitoring and land subsidence. Some of the cracks run for nearly 2 miles, slicing through desert plains, and in some cases passing alarmingly close to roads, power lines, and even agricultural zones. They cut through the landscape like scars, with vertical faces that drop abruptly, revealing the dry, fractured geology beneath the sandy surface. The terrain appears to have sheared apart in slow-motion catastrophe, frozen in a moment of violent change. What's particularly disturbing is that the areas affected show no recent earthquake activity that could account for such dramatic surface ruptures. Seismic monitors have been silent, recording no tremors strong enough to explain the sudden emergence of these deep fissures. As investigators examine the sites, a growing consensus suggests that these cracks are not solely the result of seismic shifts, but rather a more complex interaction between groundwater withdrawal, subsurface sediment collapse, and slow earth deformation exacerbated by human activity. Arizona, like much of the American Southwest, relies heavily on underground aquifers for agriculture, municipal water supplies, and industrial uses. Over decades, this relentless pumping of water from below has begun to alter the physical structure of the subsurface layers. When water is drawn out faster than it can be naturally replenished, the support that aquifers provide to the overlying sediments is lost. Without this buoyant cushion, the land can begin to sink or shift, an effect known as subsidence. While subsidence often manifests gradually as a lowering of the land surface, in some instances, particularly where geological weaknesses exist, it can precipitate more violent structural failures. The desert floor, dry and brittle after years of diminishing groundwater, is unable to resist the shifting stresses, leading to catastrophic collapse and the formation of massive cracks. These fissures are not isolated events, but seem to be linked across multiple counties. Seismologists studying the region are mapping the spread of the cracks and are finding disturbing patterns. Some fissures appear to be aligning along previously unknown fault lines or ancient structural weaknesses in the Earth's crust. These features, buried and dormant for millennia, may now be reactivating due to changes in pressure and stress fields caused by both natural and anthropogenic factors. The timing is also suspicious. These cracks are forming during one of the driest multi-year periods Arizona has experienced in recorded history. The mega-drought gripping the Southwest has not only parched the land above, but has accelerated the depletion of groundwater reserves below. With the soil desiccated and the aquifers under strain, the Earth behaves more like a brittle shell than a pliant surface. Under these extreme conditions, any shift, no matter how minor, can trigger disproportionate effects, from subtle warping to violent splitting. Seismologists have begun using advanced imaging technologies like interferometric synthetic aperture radar INSAR to detect subtle changes in ground elevation across Arizona's desert regions. These satellite-based methods allow scientists to see where the land is subtly moving before visible cracks even form. And the data has been unnerving. Small but consistent ground movement has been detected across wide areas of southern Arizona, movement that corresponds closely with the locations where fissures are now opening. In some zones, the ground has been sinking at rates of several centimeters per year, enough over time to destabilize the upper layers of the crust. What adds a deeper layer of unease to this phenomenon is its unpredictability. These fissures aren't forming in one neat area that could be isolated and studied. Instead, they are popping up in new locations with little warning, often without the kind of seismic precursors that typically herald geologic change. Farmers have discovered them cutting across fields that were perfectly level just weeks earlier. Hikers have stumbled upon them mid-trail, finding deep crevices where there was once flat desert floor. The randomness of their appearance makes prediction difficult, and mitigation even harder. Even more confounding is the sheer size and scale of some of these fissures. In one location outside Pinal County, a crack spans over 1.8 miles in length and varies between 10 and 30 feet deep. The chasm appears as if the ground has been physically pulled apart, exposing jagged layers of sediment and rock that have not seen the surface for thousands of years. The edges are sharp, unstable, and dangerously prone to collapse. Dust and debris continue to slough off the sides days after the initial rupture, giving the fissure a sense of being alive, shifting and expanding long after it first appeared. The implications for infrastructure and safety are profound. Arizona's rapid urban expansion has led to the growth of cities, highways, and utilities throughout the desert. With fissures forming unpredictably, existing structures could be at risk without early warning. Roads that cross newly formed cracks become hazardous, and pipelines, fiber optic cables, and underground utilities may be sheared or displaced by ground movement. In agricultural areas, irrigation systems and field alignments suffer disruption, not to mention the potential for injury to workers and residents encountering these geological hazards without warning. Beyond the physical dangers, the cracks symbolize something even more disquieting, a geological system in flux, possibly reacting to pressures that have been building silently for decades. Human activity, particularly the relentless demand for water in an already overtaxed environment, appears to be acting as a geological catalyst. This interaction between human needs and Earth's structural integrity is manifesting in dramatic, visible ways. Testament to the idea that even seemingly stable regions are subject to profound change when underlying balances are disturbed. Some experts worry that the fissures may be part of a longer-term trend, a symptom of a deeper structural weakness forming under the desert crust. As more water is extracted, as temperatures climb, and as rainfall patterns continue to fluctuate, the underlying conditions may only worsen. The land could become more brittle, more prone to sudden failure. These fissures, then, may be just the beginning of a series of geological transformations that will reshape the region over the coming decades. As geologists and seismologists rush to study and map these formations, they face a daunting challenge: how to model and predict a phenomenon that has no clear precedent in the local geologic record. Unlike earthquakes or volcanic eruptions, which can sometimes be anticipated through patterns and historical data, these fissures emerge silently, with no seismic rumbling, no audible warnings, just a quiet, catastrophic shift in the land. One particularly troubling discovery involves the possible connectivity of these cracks to deeper subsurface fault systems previously considered inactive. If these faults are becoming reactivated, not by tectonic movement but by stress redistribution caused by human-induced land deformation, it could signal a broader geodynamic response to surface changes. The Earth's crust, even in quiet regions, is a delicately balanced system, and significant changes in weight distribution, fluid dynamics, and pressure gradients can awaken long-dormant features. If that's what's happening beneath Arizona, then the current fissures might only be precursors to even more extensive deformation in the future. The scale of this emerging phenomenon has captured global scientific attention. Researchers from institutions across the world are requesting access to satellite data, field measurements, and soil samples taken from the Arizona sites. There is a growing interest in comparing Arizona's fissures to similar, though less severe, crack formations in other arid regions such as those found in parts of Mexico, China, and Africa. The goal is to determine whether there is a global pattern, an indicator of environmental stress points where human activity and climate change are interacting with geology in unexpected, possibly irreversible ways. On the ground, the visual impact of the cracks is jarring. Towering cacti stand precariously at the edges of new chasms, their roots exposed, some toppled into the void below. Wildlife habitats are interrupted, and the ancient desert ecosystem, a realm shaped over millions of years, is suddenly forced to accommodate violent man-made shifts. The quiet beauty of the desert, often defined by its stillness and sense of geological permanence, now feels unstable and in motion. The ground itself no longer trustworthy. What's especially unsettling is how silent the process can be. Some of the largest fissures opened up without anyone hearing a sound. No booms, no shakes, just the sudden realization that the land has changed. Surveillance footage in one affected area shows no visible movement until the ground is suddenly different. A clear line split where none existed hours before. It's a ghostly kind of destruction, creeping yet sudden, the kind that leaves little time to respond. Seismologists, geologists, environmental engineers, and policymakers now face the challenge of grappling with a threat that is both geological and anthropogenic. The Arizona desert, once considered geologically passive, is revealing its potential for upheaval. Not through earthquakes or volcanic activity, but through a slow-motion breakdown driven by environmental mismanagement and natural stress. Understanding and responding to these mysterious cracks will require not only scientific insight, but also a new vision for how humans coexist with the land, especially in regions where water, heat, and fragility intersect. The Arizona fissures have become a symbol, an early warning sign carved into the earth itself. They speak to the immense forces that lie beneath even the calmest landscapes and serve as a potent reminder that human impact on the environment is not limited to the surface. It penetrates deep, shifting the very foundation of the world beneath our feet. As these cracks continue to form, scientists remain vigilant, aware that they may be standing on the edge of an unfolding story that reaches far beyond Arizona's dusty deserts, into the core of how the planet reacts when pushed too far. Beneath the baking sun and stillness of the Arizona desert, the ground is whispering signs of change, subtle, persistent, and growing in urgency. The mysterious fissures that have split open this parched landscape have not only disrupted the terrain, but have now begun to affect patterns of subterranean behavior previously thought to be stable. As researchers dig deeper, literally and figuratively, they are beginning to understand that these cracks are more than just dramatic scars across the earth. They may be indicators of a more profound transformation underway within the lithosphere, driven by a combination of long-overlooked processes that now demand immediate attention. Beyond the surface chaos, there lies a system of pressure redistribution that is occurring far below what is visible to the naked eye. In geomechanics, the balance between compressional and extensional forces within Earth's crust is what keeps tectonic blocks in relative harmony. The Arizona fissures have introduced a new stress regime, where vertical shifts in land due to overdrawn aquifers and persistent desiccation are beginning to affect lateral tension. Seismologists are exploring whether these emerging fissures are not just passive collapses of dry soil, but part of a larger shearing event, where underground materials are being pulled apart horizontally. This kind of movement, termed tensional failure, can signal a much broader scope of deformation, suggesting that the crustal behavior in this region may be transitioning into a new mechanical phase. One of the areas under heavy scrutiny is the relationship between the sedimentary basins beneath Arizona and their capacity to absorb stress. These basins, once ancient lake beds or floodplains, are composed of loosely packed silt, clay, sand, and gravel, materials that lack the cohesion of metamorphic or igneous rock. Over the years, as groundwater has been withdrawn from these layers, air replaces water in the pore spaces. Without hydrostatic pressure to counteract the gravitational pull, these unconsolidated materials collapse inward, causing land to sink. However, this sinking isn't always uniform. When different regions subside at different rates, a phenomenon known as differential settlement, it creates stress concentrations at the boundaries. It is precisely at these transitional zones that some of the most extensive and dangerous fissures have formed. What has shocked researchers further is the temporal irregularity of these fissures. They do not seem bound to seasonal moisture cycles or even major weather events. Cracks have emerged in midwinter, during the monsoon season, and in the height of summer, showing little allegiance to atmospheric influences. This unpredictability has made real-time monitoring essential, with a new wave of ground-based laser scanners and pressure sensors being installed in high-risk areas to detect any preliminary movements or soil shifts that could precede a rupture. Some scientists are now treating these regions as living geological laboratories, constantly changing, offering real-time feedback on how the land reacts to both visible and invisible forces. In the realm of hydrology, another layer of concern is surfacing. With these fissures altering the topography even slightly, they are changing the way surface water behaves during rare desert rainfalls. Arizona's flash flood events are notoriously swift and dangerous due to the land's inability to absorb water quickly. Now, with deep trenches running through formerly flat areas, water is rerouted, pooling in unnatural depressions, sometimes near critical infrastructure or residential developments. These newly created basins can become ephemeral lakes, breeding grounds for mosquitoes, or worse, channels that direct floodwaters toward communities not previously considered at risk. Moreover, the fissures can act as vertical conduits, drawing polluted surface water down into aquifers that were previously insulated from contamination. This rapid intermixing raises serious water quality concerns for a state already facing scarcity. As experts expand their observational efforts, they are deploying microseismic arrays to detect even the tiniest subterranean tremors. These microquakes, often too faint for human senses or traditional seismographs, can offer valuable insight into how the subsurface is adjusting to changes above and below. In multiple locations near the fissure zones, swarms of microseismic events have been recorded, suggesting a creeping instability beneath the ground. It appears that the land, once in stasis, is now in motion, not with the violent release of tectonic energy, but with the unsettling quiet of a system breaking down incrementally. One key concern is how these fissures might interact with buried infrastructure such as fuel lines, aqueducts, and communication cables. Much of Arizona's subterranean network was designed under the assumption that the ground was stable, an understandable assumption given the region's low seismicity. But those design standards are now being reevaluated. In Pima and Pinal counties, engineers have begun reassessing pipeline stress tolerances, fearing that long-term ground movement, even at a centimeter per year scale, could introduce dangerous shearing forces that might rupture critical conduits. For fiber optic systems buried under newly unstable soil, the implications are different but no less severe. Shifting land can create fiber bends or breakage, leading to data loss, communication outages, and increased maintenance costs, especially in areas that were never engineered for geological volatility. Even above ground, the visual and psychological impact of the fissures is not to be underestimated. They create a sense of betrayal in the landscape, turning familiar paths into hazards and leaving people uneasy about what other hidden forces might be lurking underfoot. Entire ranches have found their access roads split, with vehicles unable to cross without costly rerouting. Trails maintained for generations by Native American communities are now interrupted, with ceremonial sites and sacred grounds rendered inaccessible. The cultural dimension of the fissures cannot be ignored. For many indigenous groups, the land is not simply territory. It is memory, identity, and spiritual connection. The sudden fracturing of the earth feels to some like a rupture of history itself. Another unexplored angle that is slowly gaining attention is the role of geothermal gradients in the region. While Arizona is not traditionally known for volcanic activity, subtle shifts in thermal conductivity have been detected near some of the more active fissure zones. Whether this is a cause, effect, or coincidence remains unclear, but thermographic mapping from drones has shown warmer than average subsurface anomalies in narrow bands parallel to some of the newest cracks. Some researchers theorize that as groundwater is removed, it disrupts natural thermal insulation, allowing latent geothermal heat to rise more freely. If true, this could compound structural weaknesses in the crust, especially where hydrothermal alterations have weakened rock formations over geological timeframes. Newer interdisciplinary studies are emerging from this phenomenon, bridging geology with remote sensing, civil engineering, and environmental science. Machine learning models are being trained on satellite imagery, weather patterns, and ground sensor data to predict where the next fissures might emerge. Early results are promising. One model correctly predicted 2 new fissure formations within 50 meters of their actual locations, purely from soil composition data and groundwater withdrawal records. These predictive tools could become vital assets for city planners and emergency services, providing advance warnings that could prevent property damage and save lives. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Arizona cracks? Will they grow or stop soon? We want to hear from you. Thank you for watching and see you next time.